الاول. So it's a recording for grade 11 advanced, just covering the questions in the exam coverage for term 1 for grade 11 advanced. So here we go with the first question or first bullet. We have to represent a point in 1, 2, and 3 dimensions in space in terms of its Cartesian coordinates. So of course, if we have only one x, so of course this is an example of one dimension. Okay, it will be 1D. Here in the second picture, it's about 2 dimensions because we have only 2 axes, the x-axis and the z-axis. It could be the y-axis. Okay, so here the vectors have 2 components. So for example, here vector A have 2 components. One on the x-axis, the other one is on the z-axis. Here also I forgot to tell you, point P have only one component because it's only one dimension. Here in this figure, because we have 2 axes, so each vector has 2 components. Coming to here, so we have 3 dimensions. If you notice, we have the x-axis, the y-axis, and the z-axis. 3 dimensions. So of course, any point on this graph or in this figure should have 3 Cartesian coordinates: px, py, and pz. Here is an example from our question 199 that asking us to calculate the length and direction of a vector, okay, in 2 dimensions. Okay, so we have to sketch the vector with a component A. Vector A, for example, have a component AX and AY, which is 30 and minus 50, and vector B, which is minus 30 plus 50 meter, and find the magnitude of these vectors. So how to calculate the magnitude of such vectors? We have to do the square root of each component squared. So for example, here A, we have AX and AY. So AX will be squared and AY will be squared as well. All of them under the square root. Okay, so you do the calculation. You're supposed to get 58.3 meters. However, B supposed to have also the same length. Why? Because both have the same component but in different directions. So for example, here 30, 50 for vector A, also for vector B 30 and 50, but not on the same direction. So that's why both of these vectors will have the same length, same magnitude. What about this point? We have to find the angle between 2 position vectors in the Cartesian coordinates. So here asking us to find not only the magnitude but also the angle. So they gave us 2 vectors A and B in 3 dimensions. How do I know? Because for vector A have 3 components, 4, 2 and 5. So first step is to know the scalar product of the vector. So A dot B, so here we are multiplying vectors. So A dot B equal the magnitude of A multiplied by the magnitude of V multiplied by cosine the angle. So in this question asking for the angle. So I'm interested in the cosine, the angle. So cosine will be, after arranging it, it will be A dot B divided by the magnitude of each vector alone. Okay, so first step, so that's the equation. So as how to proceed? First step, I start by calculating the magnitude of A and then magnitude of B. So how to do that? If you go back to the previous slide, the same way. So each component squared. So for example, here for vector A, it's 4 squared plus 2 squared plus 5 squared, all of them under the square root. And the answer is 6.7. Same thing is applied for vector B. Approximately the same length, same magnitude. So that's for the magnitude of A and magnitude of V. So we still have something to do. Okay, we're not finished yet. So we have to calculate A dot B. So how to do that? There is an equation for this. So A dot B equal AX BX plus AY BY plus AZ BZ. Okay, so that's how we calculate the product of 2 vectors. Okay, so we all have the components of A for vector A and vector B. So we multiply the x component. So for example, AX BX plus AY BY plus AZ BZ. We addition all these answers. So 4 multiplied by 4.5, then 2 multiplied by 4 plus 5 multiplied by 3. And the answer is 41. Now we have everything. We have all the components. We have the magnitude of vector A and vector B. We have their product. Now we do the division. So this will be the last step. So to calculate or to know the cosine, the angle, we just replace their values. And the answer is 0.91. But this is not the angle. So to calculate the angle, we have to do on the calculator shift cosine of 0.91, and the answer is 24.7 degree. Sorry, 24.7 degree. So here moving to question 4. So we have to multiply a vector with a scalar. We have to add or subtract vectors using the Cartesian coordinate. Here they gave us example of question 176. So we have to find the vector C that satisfy the equation. So we have x, y, and z here also equal to x and y. So we have to arrange this equation in a way to calculate vector C at the end. So just about arrangement. So we have to add the x together, y together, and then z together to know at the end what's the value of vector C. So here I just write the equation, and then as a second step, I put all the x together and the y together on one side. Okay, so minus 7x. I bring 3x to the other side, it's minus 3x as well. So plus 14y, I bring 6 to the other side, so now it's minus 6. Okay, and here minus 10z, bring it to the other side, it's become plus 10z. Now we add the x together and the y together. So we have minus 10x plus 8y plus 10z. So that's the component, that's the three components of vector C. Moving on to here, we have to calculate the speed, the magnitude of instantaneous velocity, calculate the average speed and average velocity given a graph of a particle's position versus time. Okay, so for this we choose this question, which is example 2.1. So during the time interval between 0 and 10, the position of a vector of a car on a road is given by this equation, a plus bt plus ct square, where a and b and c have each its own value. So what's the car velocity? So we have the position in respect to time. So how to do the velocity? So and then they're asking us to do the average velocity. So as a first step, you have to know, so to move from x to v2 acceleration, we have to derivate. Okay, this is highly important. So if they gave us like this example, the x function, and they ask us to calculate velocity, so we have to derivate. Also, we have to derivate in case we are moving from velocity function to acceleration. So we have also integration if we are moving the other side from a to v and then from v to x. So here we have to integrate. So here it is the function of x, a plus bt plus ct square in this example. So to calculate v, we have to derivate. So it's derivative of x over time, over derivative of time. So we just replace the equation. Now we do the derivative. So why did now I applied a replaced by 0, because the derivative of any number a, here it's in this case 17.2, the derivative of this is 0, plus derivative of bt. So here we get rid of the t and we still have the b, plus ct square. So the power which is above, we bring it as a coefficient, we bring it down, so it's now becoming 2ct, and the power it's minus 1, so 2 minus 1, which is 1, we don't write 1 for the power. So the derivative of this function, it's b plus 2ct, and now we do the replacement. For b it's minus 10.1, and for c it's 1.1. Okay, so that's for the velocity. Okay, so as a function of time, that's how they ask for this in the first question. So what's the car's velocity as a function of time? Now asking for the car average velocity. So to do that, or the average velocity, we first of all have to refer back to delta x over delta t. So we mainly have the function of x. So we just replace the time, which is 10 seconds, in the equation of x. Okay, so x, I write it x10 and x0. Okay, x0 means also we replace the time by 0. Okay, over delta t, which is 10 minus 0. So just a quick replacement, x10 by a simple calculation, you'll get it by 26.2, and x0 by replacing the time by 0 value in this equation, you will get 17.2. Okay, and then you divide it by 10. So you subtract these two values and then you divide by 10, and the average velocity in this case is 0.9 meter per second. Moving on to this question, which is 2.49, okay, we'll see. So the velocity as a function of time of a car is given by this equation, at squared plus bt, where a and b are given like the previous question. If the car starts at the origin, very important, car starts from the origin, what is the position? So what do you think we have to do here? So here they're asking us to do the integration or integrating the function. Okay, so if we already have the function of velocity and they ask us the function of position, so in this case we have to apply the integral. Okay, so first step, so and that's the function of velocity, at squared plus bt. So position is the integral of velocity as we discussed. So the position again is the integral. What's the symbol of the integral is like that. It's a symbol of s. So to calculate the position again, we have to integral or apply the integral for function of velocity. Okay, so let's do it together. How to do the integration? So we first of all I replace the velocity by the function, which is at squared plus bt. Now for the integration, we have its opposite to the derivative. So in this case, we have to add 1 to the power. So it's 80 cube over 3. Okay, because we add plus 1 to the power and then we divide by the same number. Okay, here is also the same way, applied the same way. bt, so the integral of bt, it's bt square, because we already have 1 here. So 1 plus 1, it's 2, divided by the same number 2. Okay, plus x0. We always add a constant or add a value when doing the integral. But here, guess what? They told us that the car starts at the origin. So this means that x0 is equal to 0. Okay, no value for x0, but we still have to write it. Okay, so now we do the replacement. A, which is in this case 2, so it's 2 divided by 3 multiplied by the time cube. Time is 3 seconds, so 3 to the power of 3. Plus half, B also, B is 1. Okay, it's 1 over 2 multiplied by the time squared. Okay, and the answer for this question is, or the position, it's 22.5 meter. Moving to this slide, interpret the motion of an object from its position time graph. Interpret the motion of an object from velocity time graph. So here we have, in the red line, we have the acceleration, which is constant. As we see, it's a straight line, a straight horizontal line. Then we have the velocity, which is in the blue, and then the x, which is the green curve. So first step, starting with this, because we have constant acceleration, as you see, it's a constant, same value all the time. So in this case, the velocity have to increase. It's a must. So when we have a constant acceleration, velocity have to change linearly, okay, according to a line. Okay, in this case, it increases. Also, what about the position? So object is moving in curvilinear path. So that's the deduction, or that's the reasoning, how to think whenever we have a constant acceleration. So a question for that, we choose multiple choice question from here, 2.12. The figure describes the position of an object as a function of time. Which one of the following statement is true? So first step, here we have to read carefully the graph. So we have its position time graph, where the position is constant until 3 seconds. So this means that this object still remain on the same place for 3 seconds, and then is moving, okay, changing its position. Okay, so let's see. The position of the object is constant. It's constant till 3 seconds, but not for whole the graph. So first option is wrong. The velocity of the object is constant. Not really, because here at the beginning, the velocity was 0, and then we have another value of velocity. Okay, so we have two values for velocity here, so it's not constant. So B is wrong as well. What about C? The object moves in a positive x direction until 3 seconds, and then at rest, no, it's just the opposite. The object is not moving in the first 3 seconds and then start to move. It's opposite to this statement. What about statement D? The object is constant until 3 seconds, yes, and then begins to move. True, that's true. D is correct. So A, B, C are wrong. D is correct. What about E? The object move. No. When they say move from t0 to t equal 3, which is you already know without continuing the statement that you already know that E is wrong. When they say the object moves in the positive x direction from t equal 0 to t equal 3, so you can figure out that E is also wrong. Moving on to this slide, determine an object change in velocity. So I move to this point because I know it's relevant to that question. Okay, so determine the object change in velocity by the area under the curve. So for example, if we have a velocity time graph like here, if we are talking about a velocity time graph, the area under the curve is the area. It's the position. We are talking about the position. So again, if we have a velocity time graph, the area under the curve, it's about the position. What if we have acceleration time graph like here in the blue? So the area in this case, it's about the velocity. Okay, it's highly important. It's about the velocity. Let's do an application on this from question 42. So a fellow student found in the performance data for his new car the velocity versus time graph shown in the figure. Okay, so we have a velocity time graph divided into 3 parts: 1, 2, and then 3. So the first part, to find the average acceleration of the car in all segments, 1, 2, and 3. So we have to calculate the acceleration in this case. So how to do that? We have the velocity. It's velocity time graph. So how to do the acceleration? We just calculate the slope. So in this case, acceleration for part 1, which is delta v over delta t, the slope. We choose 2 points, and then I deduce. So it's 30 minus 0. So y2 minus y1 over x2, which is in this case 6 minus 0. So 30 divided by 6, it's 5. In the second segment, acceleration is 0 because the velocity is constant. The velocity, okay, is the same. So there is no acceleration in this case. So acceleration here is 0. What about the acceleration in the third part? You apply the same way. You calculate the slope, and here you have to get, or you choose 2 points, and the answer have to be negative because here the car is slowing down. So in this case, the acceleration have to be negative. Moving on to the question B. So what is the total distance? Of asking for distance, you only have the velocity time graph. So remember in the previous slide, we talked about the area under the graph. So if we have velocity time graph, I'm interested in the distance, so I only need to calculate the area under the graph. So if you see here, we have a triangle. Remember area. What's the area of a triangle? It's half multiplied by the base multiplied by the height. We have also another triangle here, if you notice. We have another triangle here. Okay, but of course with different values. Okay, and we have, if you notice here, we have a what? We remained with a rectangle. Okay, so let's calculate the distance by calculating the area. So the total distance, it's the area under this line or under this curve, okay, in the velocity timing graph. So for the triangle A1, we call it A1, area 1. So it's half multiplied by the base. What's the base here in this case? 6. Half multiplied by the base multiplied by the height. The height is 30. Okay, so area is 90 meter, or the distance covered in the first part, it's 90 meter. What about the 3? I jump to the 3. It's half the same way. Base, what's the base between from 12 to 24? The base is 12. Okay, it's not 24, don't be mistaken. It's 12 multiplied by the height. The height is also 30 meter per second. Okay, you do the calculation and you get 180 meter. What about the second area? Here we have a rectangle. The area of rectangle is pretty easy. It's just the width multiplied by the length. So it's 6, from 6 to 12, it's 6 multiplied by the height, which is 30 again. So you add all these values and then I think you get 450 meter for this question. That's the total distance covered under this graph. Now moving on to question 7. Okay, interpret the motion of graph object under free fall. Okay, so it's about a free fall. We have initial velocity of 26. So someone is tossing a ball. Initial velocity is 26.4. So asking how long it will take. How long means talking about the time. Okay, so the velocity, initial velocity, it's about free fall. So of course, A is always downward. If you see here, if you notice in the black, in this black vector, small black vector, A is always constant, which is downward. It's minus 9.8. So how long? It's about the time. But remember, they give us the velocity, initial velocity. So because of the symmetry, you see the symmetry in the graph. So the initial velocity, which is 26.4, it's equal the final velocity, but in different direction. So this is about the symmetry. So the same speed that you throw the ball with, when the ball will fall down on the same value, on the same speed, but in opposite direction, of course. So that's why we can write that Vf, the final velocity, equal the initial velocity, but in opposite direction. So it's minus. Okay, so now remember asking us about the time. So we know now the initial velocity, we know the final velocity, and we know the acceleration. So the equation that we can use is Vf equal Vi plus At. I'm interested in time, so I arrange the equation in this way. So T will be equal to Vf minus Vi over the acceleration. Remember Vf, yes, remember Vf is equal minus Vi. So minus Vi, and here we already have minus Vi, so we have 2 minus Vi over the gravity. Okay, minus the gravity is minus and minus. Okay, they cancel each other. So it's 2 multiplied by Vi over the gravity. And the time taken for the ball to go up and fall down again, it's 5.38 seconds. Now, moving to question or bullet number 10, I'll discuss about bullet number 9 in different slide. So in this part, we have to apply the relationship between particles' position, velocity, and acceleration as measured from two reference frames that have that move relative to each other at constant velocity. Okay, along an axis. Okay, for this I choose this famous example of 3.63. You are walking on a moving walkway in the airport. The length of the walkway is 59.1 meter. The length of this walkway. If your velocity, so if you are on the walkway and you are moving, you're already moving, your velocity is 2.35 meter per second. You're already walking. And the walkway is also moving at a speed of 1.77 meter per second. So how long, again, how long means the time. How long it will take you to reach the other walkway. So asking for the time. So first of all, we write the given. We have the length, 59.1, initial velocity, final velocity, and the time. Okay, so in this case, distance equal velocity multiplied by the time. So time in this case is of course distance over the velocity. So distance is given, but what is the velocity, total velocity? Is it 2.35? Is it 1.77? Okay, or is it both of them? It's the total velocity. Okay, so time in this case is the distance over the total velocity, which is it will take you 14.3 seconds to cover this whole distance. Here in this question, calculate the particle's position, displacement, and velocity at a given instant during the flight given launch velocity. So for this bullet, I choose this question 3.1. Okay, this multiple choice question. So you have an arrow which is shot horizontally from a speed of 20 meters per second from a top tower. So this is the tower. You are throwing a ball. Of course, the ball will fall down or cover a certain distance. So the time to reach the ground will be. So we're not sure about the timing. So that's why they gave us multiple answers. So we'll figure out. So remember, we are shooting the ball horizontally in this way. Okay, so that's the ball, the vector velocity, initial vector velocity in this way, and the ball will follow a curvilinear trajectory to fall on the ground. Okay, so how to start solving this question? First, this is the y initial, which is 60 meters. It's given. This is the y final, which is 0 because the ball reached the ground. So again, time is the unknown. So what equation to use in this question? So we have the initial velocity, we have the initial height. Of course, we know the acceleration because it's a free fall, and asking for the time. So what equation in physics that cover all these parameters together? Yes, that's it. So y final equal y initial y0 plus v0 yt minus or plus half. Here you can write minus gt square or خلاص, the way it's written here, minus half at square. So remember, y final, because the ball reached the ground, it's 0. Y initial, it's 60 meter. It's 60. And because we are talking about the y-axis, that's why I replace x by y, because we are working on the y-axis. Okay, so v0y, you already know v0y at the highest point. So this is the highest point here, and the balls start to fall on the highest point. Initial velocity on the y-axis is 0 as well, so v0y here also is 0. Okay, so we can write it this way: 0 equal 60, that's the highest point, plus v0y, which is 0 as well, okay, minus half g t square, or sorry, minus half at square. Okay, I'm interested in the time, so time will be square root of 2 multiplied by the 60 divided by 9.8. So it will take 3.5 seconds to hit the ground. So I choose for this option C. Moving on to the next part, here describe object in static equilibrium, dynamic equilibrium. Okay, so it's about friction. So for this bullet, I choose question number 81. So a block of mass of 5 kilogram is sliding at a constant velocity down an inclined plane that makes an angle of 37 degree. Okay, so this we have an inclined plane of 37 degree with respect to the horizontal. Okay, so what's the friction force in this case? Okay, so what's the friction? So the given, okay, let's write the given. Okay, sorry. So we have the angle, we have the mass. So first step, you have to know that the mass is sliding on the x-axis. It's tilted a little bit, but it's on the it's on the x-axis. So because it's moving at a constant velocity, so we are applying Newton's second law, okay, which is F net equal to 0. Okay, it's on the x-axis, F net x equal to 0. Okay, so what are the forces on the x-axis? It will be the friction. The friction is on the x-axis, but it's in the in this direction, and we have a part of the mg. Mg means the force of gravity. So part of the force of gravity is also on the x-axis. So that's why we use mg sine the angle, and it's negative because it's downward. Okay, so it's minus mg sine the angle because it's opposite to the angle, so we use the sine function. So minus mg sine the angle plus the force of friction equal to 0. Okay, remember we are interested on the force of friction, so I need to calculate F. So F is equal mg sine the angle. So mass is given 5 kilogram, gravity, and sine the angle, which is 29 Newton in this direction. So we already calculated the friction force. Now moving on to the second part, calculate the coefficient of kinetic friction. So that's the coefficient of friction mu. We have to calculate mu. Okay, so to calculate mu, we have to go back to the normal force N, because mu and N are related by this equation. Force of friction already calculated in part A equal mu N. So mu is the question here, and N we have to calculate. So here, moving from x-axis, now I'm interested on the y-axis. Why? Because N, the normal force, is on the y-axis. So I have to work on the y-axis. Also, because the object is not moving on the y-axis. There is no motion on the y-axis. So we can apply also Newton's second law, where F net is equal to 0. What are the forces on the y-axis? Of course, it's the normal force, and in this case, part of the force of gravity, in this case, it's mg cosine the angle. Okay, it's downward, so it's minus mg cosine the angle. So N is equal to mg cosine the angle. So we know the normal force. We calculate now the normal force, and we replace it in this equation to calculate the mu, because F is already calculated in part A. So to do that, let's replace equation 2 in equation 1. Just replacement. So now it was, first of all, F equal mu N. So instead of N, we replace it by mg cosine the angle. So it's mu mg cosine the angle. Okay, so I'm interested in mu, so mu is F over mg cosine the angle. So it's F, which is 29, okay, already calculated in part A, over mg cosine the angle. So in this way, we calculated the coefficient of friction, which is 0.75. Moving on to this bullet about the air resistance. So apply the relationship between the drag force and object moving through the air. So here we take the example of a skydiver, okay, jumping into the air. So after a certain time, the skydiver will reach a certain velocity or a constant velocity. It's called terminal velocity. So what about this terminal velocity? When the force of gravity, mg, is equal to the force of the air pulling the skydiver upward. Okay, so as you notice, here we only have the force of gravity, which is downward. Here the drag force starts to increase to a time where it's equal to the force of gravity. In this time, or in this case, okay, the velocity of this person will become constant. Okay, so how to do that? We already know that the drag force of, or force of the air, is equal kv square. K is a constant, and we'll see, multiplied by v square. So applying Newton's second law here, because it's opposite to each other. So the drag force in the blue, it's up, and the force of gravity in the red is down. So force of the air up minus mg equal to 0. Why 0? Again, because it's a constant velocity, terminal velocity. Okay, Newton's second law. So we replace the force of the air by kv square minus mg. So you replace it or you arrange it. So now you can know that velocity, or vt, or we call it terminal velocity, it's equal to square root of mg divided by k. Moving on to this question. So in this question, we have to identify that the direction of the force due to pull on the ropes act exactly on the direction along the rope. Okay, and describe how the forces with which we pull on the massless rope is transmitted through the entire rope unchanged, even if the rope passes over a pulley. So there is a famous example here, in example 4.2. Okay, so we have on a table, we have two masses. One is suspended, mass 2, and one is on the table, m1. Okay, so let's discuss each force alone, or each mass alone. So for m1, what are the forces applied on m1? We'll see. So m1 is moving, okay, or accelerating. Okay, so asking for acceleration. So of course we apply Newton's third law, where F net on m1 is equal m1a. Okay, so what are the forces applied on m1? So it's the force of gravity, of course, which is downward, as you see here. This is M1, force of gravity downward. We have the normal force because it's on the table, it's upward. And we have tension by the rope, it's to the right, equal MA or equal M1A. Okay, so I'm interested in the tension force. So tension, so equal M1A. Why? Because usually the normal force in this case and the force of gravity, they cancel each other. So in this case, the tension or the rope tension is equal M1A. Okay, so that's for the first mass. What about the second mass? What are the forces on M2? So M2 is moving on the y-axis. It's moving up and down. So what are the forces on the M2? So it's F net equal M2A in this case. Again, because it's accelerating. So F net equal M2A. F net or the total force. So here we have two forces again. It's the force of gravity down, M2G, and we have the tension force, which is up. So we can write T equal M2G equal M2 minus M2A. Why? Because the object here or the square is moving downward, equal M2G. Okay, so now we arrange the equation. So now we have two equations of tension, equation 1 and equation 2. So in this case we can write them equal because of course T, tension on the first, equal the tension on the second. So we can write M1A equal M2G minus M2A. Then that's what we did here. So M1A equal M2G minus M2A. And that's how we calculate the acceleration in this example. So this, you can only apply this if we don't have friction. Okay, so we can write A equal M2G over the total mass M1 plus M2. Okay, M2, remember M2, which is the hanging mass, always have to be in the numerator. M2G over the total mass M1 plus M2. Now, what if we have friction? Okay, what if friction is applied in the same example? Okay, so the same equation, A equal M2G over the total mass, but in this case we have to subtract the friction. So it's A equal M2G minus the friction force, which is mu-n over M1 plus M2. Okay. Next, so in this slide, we have to position vector has a length of 40 meter and an angle of 57 degree above the x-axis. Find the vector component. So we have to draw first the vector, which is vector L. Okay, two dimensions x and y. So find the vector's component means we have to find Lx and Ly. So I call it vector L to simplify things, and then it's divided into Lx and Ly. So has two components as discussed as Lx and Ly. So this is, if you see the triangle here, we have the triangle. So Lx is adjacent to the angle. So if this is the angle, Lx of course is on the x-axis. Okay, so we apply, because it's adjacent, we apply the cosine function. So cosine the angle equal adjacent side over the hypotenuse. What's the adjacent side to the angle here? It's Lx over L. So by simple calculation, Lx will be equal to L, which is the hypotenuse in this case, multiplied by cosine the angle. So the answer is 21.8 meter. That's for Lx. Now what about Ly? So Ly is opposite to the angle. So this is Ly. So because it's opposite, we apply the sine function. So sine equal Ly over the hypotenuse. Okay, Ly over the hypotenuse L. So Ly equal L sine the angle. It's L, the hypotenuse, multiplied by sine the angle, which is, in this case, 33.5 meter. Moving to this example, we have to solve problems related to position, displacement, calculate instantaneous velocity, describe the motion of a straight line. We have to apply direction of motion, constant acceleration. Okay, so for this bullet, I choose this question. The position of a particle moving on the x-axis is given by this function, 11 plus 14t minus 2t squared. Okay, what is the average velocity? So remember at the beginning of the recording, we discussed that when we have the position function and we have to move on to the velocity function, so we only have to derivate in this case. So this is the function of x. Okay, so but here we have time limit between 0 and 4. Okay, we have values for the time, so we either find or replace the time in the x function and then apply this equation, which is velocity equal delta x over delta t. Okay, so x final minus x initial. The final in this case is considered as 4 seconds. So we replace 4 seconds into the function of x and you get 35 minus the initial time, which is 1 second. We replace it in x. So the answer is 11 over t final minus, here it's supposed to be 1, sorry. It's 4 minus 1, so the answer is 6 meters per second. Moving on to this question. 27. So an object moving in xy plane where the x and y of the object as a function of time are given by the following equation: 4.90 squared plus 2t plus 1. Okay, and y function of time also it's 3t plus 2. So what's the velocity? Again, we have the x component and y component asking for the velocity. Okay, and then ask for acceleration. Okay, so let's see. So that's the function, the main function. To calculate the velocity, of course, we have to derivate. How to derivate? Again, we multiply the power by the coefficient. So in this case, 4.9 multiplied by 2, t, plus, here we get rid of the time, t. So we get rid of t, and then we remain with 2. And derivative of 1, it's 0, so no need to write it. So, and then, the velocity function of time on the x-axis, it's 9.8 t plus 2. Okay, what about the acceleration? We also do derivative a second time. So remember, to do from position to velocity, you do the derivative. From velocity to acceleration, we do another derivative. So here we derivate the function, the velocity function. So it's derivative of 9.8t plus 2. Again, derivative of 2 is 0. And derivative of 9.8t, we get rid of the t. So 9.8 is the answer. That's only for x. We apply the same thing now for the y. So the function of y, it's equal 3t plus 2. So to derivate it, or to calculate the velocity in this case, it's derivative of the y. We get rid of the 2, which is 0, of course. And 3t is 3. So again, the derivative of 3t, it's 3. So now the velocity on the y-axis, it's 3 seconds. So if we do the derivative one more time to calculate the acceleration on the y-axis, it's the derivative of 3, which is a constant. 3 is constant, so the derivative of this constant is 0. Moving on to this slide, solve problems related to object, horizontal, vertical, and inclined plane in situation involving friction, as we did before. Draw free body diagram and apply Newton's second law. Okay, our solve problem related to multiple connected mass moving in a system involving friction connected by a light. Okay, so great. So for this question, for this bullet, I choose example number 4.2. So we have a player or gymnast of a mass of 55 kilogram hangs. Okay, it's hanging, means there is no normal force. Okay, so if the ropes supporting the rings are vertical, as you see here in the picture, okay, and attached to the ceiling directly above, so what is the tension in each of the ropes? Okay, so the mass of the player 55 kilogram, okay, paired of ropes. So we have 2 ropes in this case. So let's do a diagram for this question. So the tension force are upward, and the force of gravity, it's downward. Okay, so what law of Newton we are applying here? We are working on Newton's second law. Okay, so in this case, F net, because Newton is because the person is not moving, so it's Newton's second law, where F net is equal to 0. So what are the forces in the system? It's tension force. We have two of them. Okay, because we have two ropes, T plus C minus Fg equal to 0. So T plus C, it's equal to T equal to the force of gravity. So okay. Sorry, it's Newton's first law. Yes, sorry, because F net is not moving. Okay. Yes. So here for this one, so a block of mass 20 kilogram is supported by a vertical massless cable. Okay, so this is under the same bullet but with another example. So a block of mass of 20 kilograms supported by a vertical massless cable, initially at rest. Okay, not moving. Okay, so the block is then pulled upward with a constant acceleration. So it was not moving and then accelerated. Okay, we have acceleration 2.3. So what is the tension in the cable? Okay, so we are applying also Newton's law. So F net equal ma. So this is Newton's second law because acceleration exists. So F net equal ma. So what are the forces here? The tension is upward and the force of gravity is downward. Okay, tension again, it's upward, so it's plus T minus the force of gravity downward, mg equal ma, Newton's second law. Okay, so to calculate T, we just replace the mass, acceleration, and the gravity. We already know it's 9.8. So the tension, the cable is supporting a force of 242 Newton. What about B? What is the net force acting on the mass? Calculating the net force acting on the mass. In this case, the same way, Newton's second law, F net equal ma. The mass, what's the mass here? It's 20 multiplied by the acceleration, 2.32. So direct application of this equation, F net equal ma, and the answer is 56 Newton. What is the speed? Now asking for the speed. What is the speed of the block after it has revealed 2 meter? So it's v square, because here we use this equation because we don't know anything about the time. Okay, so we only know the velocity and the displacement. Okay, we have no idea about the time, so we apply this equation, v square equal v initial square plus 2a delta x. So we have the displacement 2 meter as well, so v final, the one they are asking for, what is the speed, equal v initial, okay, which is considered as 0, okay, plus 2a delta x. The acceleration is already given as well, it's 2.32 meter per second square. So the velocity of the system after moving for 2 meter, it's 3 meter per second. I believe that's it for now. I wish you whole succeed in your finals, and thank you for listening.